Welcome back. This is the third video. This is section 22, MODTRAN. The publicly available MODTRAN model simulates the emission and absorption of infrared radiation in the atmosphere. This will help us understand absorption in the atmosphere and the radiative forcing of increasing greenhouse gas concentration. You may want to play with this tool. I will take some time explaining this tool because you will see results like this in papers and websites. The following description is adapted from the MODTRAN documentation. The spectrum plot here shows the intensity of infrared light as a function of the wavelength of the light. By default, the horizontal axis is wave number in inverse centimeters, which is how these graphs are presented in climate articles. In this course, we have used wavelength for the horizontal axis, so I am switching it to wavelength. For the graph in the middle of the page, the smooth curves, like this red one, are theoretical emission spectra of black bodies at different temperatures. The average surface temperature of the Earth, 288 Kelvin, is about halfway between the top two curves. This red curve is 300 Kelvin, the legend is here, and the orange curve is 280 Kelvin, and this looks to be almost halfway between. The jagged blue curve is the spectrum of infrared light at the top of the atmosphere looking down, so energy that will escape outward to outer space. Some of the wavelength ranges are in absorption windows, and radiation from Earth's surface reaches the top of the atmosphere. Other wavelength ranges are in absorption blankets, and radiation reaching the top of the atmosphere was emitted by the atmosphere from some range of altitudes, large or small. Almost all of the jaggedness is due to water vapor in the atmosphere. The jagged curve here is blue, but later we will see it in red. This graph is not the default settings. I configured the pre-industrial concentrations of carbon dioxide and methane. 280 parts per million of carbon dioxide, 0.7 parts per million of methane. And I configured an 80-kilometer top of atmosphere altitude, and I configured the U.S. standard atmosphere locality. The total energy flux from all infrared light is displayed at the lower left and labeled as upward IR infrared heat flux in units of watts per square meter. The model demonstrates the effect of wavelength selective greenhouse gases on Earth's outgoing infrared energy flux. We will see that increasing the concentration of greenhouse gases decreases the heat flux escaping to outer space and increases the heat flux re-radiated by the atmosphere toward Earth's surface, which will cause temperature of Earth's surface and the lower atmosphere to increase, the greenhouse effect. This model does not implement the feedback of increasing the temperature, but we can check this manually to an extent. Where the atmosphere is optically thin, so pretty transparent, the infrared light comes up from the ground and passes through the atmosphere, and the light is as intense as that from a warm black body averaging 288 Kelvin. We see this in the water vapor carbon dioxide window, 8 to 13 microns, here. Remember, this model uses a single constant ground temperature. This dip is due to ozone, formed in the atmosphere by sunlight. Where the atmosphere is optically thick, opaque, looking down from space, you see nearly black body emission from the altitude that transitions from optically thick below to optically thin above. For example, the 14 to 16 micron carbon dioxide blanket band here is 100% absorbing through most of the troposphere at pre-industrial concentrations and current concentrations, and the thermal radiation reaching the top of the atmosphere has an effective black body temperature of about 225 Kelvin. You see that it's close to this blue curve, which is 220 kelvins. So presumably that infrared light is emitted primarily from the 10-kilometer altitude of the troposphere, which was the brown curve in our earlier spectra plot emission graph. Water vapor 100% absorption at 5 to 7 microns here looks to be about 230 Kelvin, presumably emitted primarily from the 9-kilometer altitude, though we did not check this with SpectraPlot. Water vapor 100% absorption at 20 to 30 microns here looks to be about 240 kelvins at 30 microns and 260 kelvins at 20 microns, presumably emitted primarily from the 4 to 8 kilometer altitude. Methane absorption is at 7.6 microns, so about here, but we can't see it on this graph. Methane is only partially absorbent at this concentration, and water vapor is partially absorbent at the same wavelengths. You can play with MODTRAN and verify for yourself which gas produces each band. We can modify the greenhouse gas concentrations at the upper left and see how it affects the outgoing infrared energy spectrum and total heat flux. Here I've used the pre-industrial concentrations of carbon dioxide and methane. The model takes into account how concentration varies with altitude, which graph we can display on the right side. This defaults to telling us the temperature as a function of altitude, but here I will change it to the carbon dioxide concentration, which is 280 parts per million at all altitudes, pre-industrial. And now I'll change it to methane. And that's the methane concentration, highest near the Earth's surface and then falling with altitude. Methane is getting decomposed in the atmosphere. It's not being absorbed at Earth's surface. We can modify the locality, which changes the ground temperature, atmospheric profiles, and concentration of water vapor, and see how it affects the outgoing infrared spectrum. I'm not going to do that in this video. You can do that for yourself. I have used the 1976 U.S. Standard Atmosphere, which seems a middle setting. A full climate model should deal with all latitudes, continents, and oceans realistically. We can modify the weather here. And see how it affects the outgoing infrared energy spectrum. I have used no clouds or rain. Any amount of cloud or rain reduces the upward heat flux at the top of the atmosphere significantly. A full climate model should deal with clouds and rain realistically, including that increased surface temperature increases the water vapor in the atmosphere, which is an amplifying positive feedback effect. But increased temperature can also change the amount of cloud cover, which changes Earth's albedo. The total energy flux from all infrared light is displayed at the lower left and labeled as upward IR heat flux in units of watts per square meter. The total energy flux is the area under the jagged curve. But beware that this is for the specific locality and weather setting we use. It is not the global average across all conditions. This MODTRAN model does not compute global warming. That is, it doesn't change the Earth temperature in response to changes in heat flux. However, we can offset the temperature of the ground and atmosphere manually here. Temperature offset. To find a first estimate for the temperature increase that would balance an increase in greenhouse gas concentration, which I will do later. However, when we offset the temperature, MODTRAN does not automatically change atmospheric water vapor in clouds. It does not implement the positive and negative feedback effects of increased temperature. The results of such models that do not implement the feedback effects of full climate models are called immediate radiative forcing. We must remember the climate sensitivity range that we learned earlier. The spectrum produced by MODTRAN seems to largely agree with satellite measurements as shown in this image, though a higher resolution model might be better. I think the wave number increment in MODTRAN is 2 inverse centimeters. We could also look upward from the ground to see the thermal radiation arriving from emission by the atmosphere. We will not use that in this course, but you can try it. Section 23, MODTRAN Immediate Radiative Forcing. MODTRAN allows us to save a configuration as background and compare a new configuration to it and report the difference in heat flux. I will compare 2022 concentrations to pre-industrial. I will save this run to background, change the carbon dioxide concentration to 420 parts per million, and change the methane concentration to 1.9 parts per million. Here the curve that we had before that was in blue, pre-industrial concentration, that curve has changed to red, and we have a new curve, jagged curve, that is in blue, although it can be hard to see. The jagged blue curve is the outward radiation at the top of the atmosphere for year 2022 concentrations of carbon dioxide and methane. For almost all wavelengths, the blue curve is equal to and behind the red curve, with little or no incremental impact on the climate. In particular, there is little change from 14 to 16 microns here, where carbon dioxide has always been 100% absorbing. However, those few wavelengths where the blue curve is lower than the red curve represent the entire immediate radiative forcing for climate change and global warming. Most of the human-caused radiative forcing is at the wings of carbon dioxide's 15 micron band. 13 to 14 microns here, you see here, you see that there's a little bit of blue below the red curve, and 16 to 18 microns here, where there's a little bit of blue below the red. This agrees with our earlier section on why additional carbon dioxide affects global warming after the center of the 15 micron band is 100% absorbing. Now, there is a spike at 15 microns, and the blue curve is slightly higher than the red curve. That wavelength has high line intensity, short absorption length, and is emitted from the top of the atmosphere. But I haven't quite figured out why the blue curve is higher than the red curve there. The substantial contribution from methane is from 7.5 to 9 microns here. You see that the blue dips below the red there and there. Where water vapor is not 100% absorption. Look carefully that the blue curve is below the red curve for those wavelengths. Try for yourself changing the concentrations of carbon dioxide and methane separately. The difference in outward heat flux at the top of the atmosphere between pre-industrial times and 2022, the area under the blue jagged curve minus the area under the red jagged curve, is reported here, difference, as negative 2.64 watts per square meter, a reduction in outward heat flux that forces an increase in temperature of Earth's surface and the atmosphere. This number is not quite correct and accurate because we use the same temperature for both times, and this model does not calculate global warming from forcing. Nevertheless, this agrees with the IPCC radiative forcing value of 2.65 watts per square meter in 2019 relative to 1750 for carbon dioxide and methane, excluding other sources. Next, I will manually adjust the temperature offset to get equal heat flux for the 2022 concentrations and the pre-industrial concentrations. So I want to put in a value for temperature offset that will make the difference go to 0. And I'm going to put in 0.655 Celsius temperature offset. And the difference went to 0. 0.655 Celsius would be the eventual temperature increase over a couple hundred years if concentrations remained constant going forward, but they won't, and the locality and weather settings were a good average for the entire Earth, but they aren't, and there were no amplifying feedback effects, but there are. In an earlier section, we used the Stefan-Boltzmann law to estimate a 0.37 degrees Celsius increase to balance a 1 watt per square meter imbalance. That would be a 1 degree Celsius increase for 2.64 watts. And we would compare that 1 degree Celsius against MODTRAN's 0.655 Celsius. So good enough for the rough estimate we made earlier. With feedback effects of water vapor in clouds not modeled by MODTRAN, we would expect an eventual 1 to 3 degrees Celsius increase over the pre-industrial temperature if we stopped emitting carbon dioxide and we stabilize the methane concentration. But it will take a couple hundred years to fully reach that temperature. Temperature has already increased by 1.1 degrees Celsius warmer than 1850, and we continue to emit more carbon dioxide and methane, and at an increasing rate. Section 24. MODTRAN projection for 2050. Let's see the impact, according to MODTRAN, with its limitations, of continued emissions until 2050 at about the 2023 emission rates. So the business as usual approach. Hopefully the world will reduce these rates, but presently carbon dioxide emission remains high. So let's assume a 70 part per million increase of carbon dioxide from 2023 to 2050, and a 0.3 part per million increase of methane from 2023 to 2050. This would be a 16 to 17% increase of carbon dioxide and methane in the atmosphere relative to 2023. So these are the 2050 configuration I've given it, and I've had it calculate relative to 2023. And MODTRAN says that there will be a difference of 0.82 watts per square meter. We get an immediate radiative forcing of 0.82 watts per square meter, which could raise temperatures eventually by a further 0.205 degrees Celsius, not including feedback effects. This could be an eventual increase of 0.3 to 0.9 degrees Celsius, including amplifying feedback effects. Carbon dioxide emission would be responsible for 80% of this additional heating, and methane emission would be responsible for 20%. This is not the temperature increase we will experience from now to 2050. The increase of temperature from now to 2050 will be mostly due to today's concentrations due to past emissions. The temperature increase due to emissions of the next 30 years will take effect over the next 100 years. Some denialists might agree that this temperature increase will occur in the future, but argue against reducing emissions now due to the cost, difficulty, and disruption of reducing emissions. Maybe the cost of reductions might decrease in the future, or emissions will decline due to market forces instead of government policies. But if we continue to emit business as usual, the eventual temperature will continue to increase. Next, I configured MODTRAN with recent concentrations. The upward heat flux at the top of the atmosphere varied by 50% when I varied locality and 20% when I varied clouds and rain. I increased the carbon dioxide concentration, and the change in immediate radiative forcing varied by up to 60 to 90%. I offset the temperature to estimate the rise in global temperature, and that rise varied by up to 50%. I take this to mean that climate scientists must use a realistic, two-dimensional model of the Earth's continents and oceans, latitudes, temperatures, clouds, and rain, but that some granularity should be good enough. This doesn't seem like a chaos or butterfly effect situation to me.